Okay, I think we can start this second session. So this session is about checkpointing. Can change slide. Yes. So obviously, before starting about this session, the first point is what is checkpointing. So let's take a simple example, and actually we'll use this example during the full talk. It's just a program that counts. So of course, the program does 1, 2, 3, and so on. And at that point, I'm killing the program with Control-C. And of course, if I'm restarting the program, the normal behavior is that this program just continue from scratch. So it's continue acting, from the beginning. If there's nothing special, it will restart from 1. So that's what we call a program without checkpointing. That's of course the default. And that's of course a waste of CPU time in a lot of cases, because what you really want is that the programs continue, that it restart actually where it stops or close to where it stops. And that's the main idea, obviously, of this talk, is how to implement that in practice, how you can use that on HPC infrastructures and have advantages of Slurm to do that efficiently when needed and stuff like that. So to put some definitions about checkpointing. So checkpointing is about saving the computations so that it can resume later rather than starting again from the beginning. So what I'm going to cover today is first some general concepts, put some word on definitions, let's say, about what checkpointing is about, and put some more motivations about checkpointings additionally. Then I'm going to introduce signals. So I'm going to probably discuss stuff that you know, but how can we use signals for doing checkpointing on demand and when it's needed? Then we use that on HPC infrastructures and with Slurms in particular. And then the last point of this talk is a program called DMTCP, which is actually checkpointing the program which is not designed for checkpointing. So basically, any program that you run can be checkpointable, even if the developer didn't do it for you, then you need to use a program like DMTCP, and we'll show some demonstrations how to do that in practice. So that's the plan for the next hour. So why do you need checkpointing? So obviously there are cases where checkpointing is completely mandatory, and that's one of those cases. It's just a quite old text editor probably now. But imagine a text editor without checkpointing where you need to restart to write your full text every time you reopen your browser. And that actually was the case probably more than 20 years ago now. When I was a kid, there was basically like that. I've seen really the text editor where you were closing your computer. If you can call that a computer at that time, then basically when you reopen it, you were forced to restart everything from scratch. So that's really the old days, obviously, but not that old. I've seen it basically. But in practice, why do you need that for HPC? And there are basically 4 points, and I'm going to quickly speak about them. The first one is wall time. So in all clusters, you have a maximal wall time. So typically it can be a couple of hours, it can be 1 or 2 days, or in some cases it's extremely long. But as a user, it's quite advantageous that the wall time is quite short, because if the wall time is quite short, the cluster will be quite reactive. And typically you will get faster the allocations that you ask for. So if the clusters allow allocations for 1 month, let's say, then you can wait basically a week before getting your allocations. And that typically, if you want to run something of 1 hour, it's a waste, obviously. So having short maximum wall time, that's beneficial for the user. But at the same time, there's a penalty here, because if your job is longer than, let's say, a couple of hours, the maximum wall time, you cannot fit your jobs within that. And that's one of the main reasons, obviously, why people use checkpointing on HPC infrastructures, is actually that some clusters doesn't allow you to run the full jobs in one block, and you are forced to basically have your job still in the middle and then restart from the last checkpoint. And that's one of the main reasons, obviously, you can do that. The second reason is more practical. Checkpointing allow you typically to save some variables, especially if it's done by the developers. Those variables are typically meaningful for your computations. And that means in case of crash, you can look at that checkpoint, try to understand what's going on, And depending, of course, of the situations, you can basically restart your code from that checkpointing or modify what's going wrong. I mean, it needs a bit of work, but you can basically try to understand why the bug was there and fix either the code or restart the program depending on what the issue is. If it's just one file is missing, you can put the file and restart the computations, obviously. A third reason why checkpointing is useful for HPC is, of course, hardware crash. I mean, you can have an FS server which is not responding. You can have some node that's rebooting because of someone else taking all the memory on the node, or whatever reason that can lead to a crash, a resource not available at a given time. And that would allow you to restart from the last checkpoint without basically needing to change anything in that case and allow you to terminate. And of course, there are quite a lot of hardware crashing clusters. There are a lot of hardware, so of course, typically it doesn't impact you very often, but it can happen, obviously. The last one, and it's quite interesting, is preemption. So basically, it's allow you, even if you don't have your full time that you request, let's say you request 2 hours, and the scheduler only see that, oh, you have only 1 hour available on that machine. If you allow preemptible jobs, then you will run for 1 hour, then your jobs will be typically suspended due to the higher priority job that need to start. And then you will wait the time that those jobs are finished. You're typically going to restart actually on other machines, on other nodes, and then your job will continue. So a job which is preemptible is actually going to run much faster. Typically, you will use better the resource. And therefore, on some clusters like NERCs, for example, if you allow your jobs to be preemptible, then you're actually going to pay less in terms of time allocations, actually. So that's both beneficial for the clusters because you use better resource, but also for you because you are typically going to run faster, and then your job is going to be at the end faster than if you have to wait. So even if here you have to wait, you have to suspend, at the end of the time, typically you are gaining time. You have your jobs faster, faster finished. So obviously, the first thing to do is to look at the documentation. So the first things most of us are typically using software done by someone else. Also, there is some questions here. So there's 2 questions. So one with preemptible jobs, when the job resumes, does it continue on the initially allocated nodes? Typically not. So typically that node will be taken by another job. So it will typically start on other nodes. I guess that's configurable. And the next question is preemptions taken into account on CC machines? No. So for the one we don't have any on our cluster, we just configure for preemptible jobs. It can be done, and I think that would be a good idea actually. But for the one that is not something that we use in the CC, but some of our clusters do. Thanks for the questions. So yeah, as I said, the first thing is as user, if I can change the slide, yes. As user, the first thing to do, obviously, is to check if your code has built-in checkpointing. That's typically the best options because the developers know exactly when is the best time to basically checkpoint your code to avoid basically to have too many information written on file, or basically when the information is minimal. And we'll do an example later, but typically it's after the end of one big iterations. If you are the developers, of course, you typically know when it makes sense for you to checkpoint your code. You have a couple of questions, of course, to ask is how much CPU it takes to create or to restart from the checkpoint? How many disks do I need to make the checkpoint? How much flexible I want to be in terms of restart? So there was the questions, oh, if I'm restarting on a node, is my work going to work or not? So that's questions you need to answer basically when you implement. And of course, at some point you will need to write additional codes, but typically not that much. So let's do a first demonstrations. It's more to show actually what the original Python code is and discuss some stuff here. So here is my demonstrations code. It's just actually a Python code, which is doing a for loop from 1 to 500. And at each stage is doing print ag. So that code is not doing anything else, okay, except maybe sleeping 1 second after each iterations. All the rest that you see here and here, that all those are only related to buffer. So since I want to do these demonstrations live, obviously, I want to see all the numbers appearing all the time. And on HPC cluster, they like to put buffer everywhere just to gain efficiency. Because typically on HPC cluster, you don't need to see everything's occurring live, and you are completely fine. If your log appears only after 30 seconds, it's perfectly fine. Here, I don't want to, for all demonstrations, to have to wait basically 30 seconds to see suddenly 30 numbers appearing. It would be quite stupid in a way. So that's the original code. So no buffering at all. Yeah, I should mention that actually. So all those examples that I'm showing here, all the scripts are available on the Indico page. On the Indico page, you will actually see one link and one table and the PDF of my presentations. So the table contains all the examples I'm going to show during my presentations, and the links is basically scripts, but in other language. So I'm mainly going to focus on Python. Actually, I'm only going to focus on Python. But if you want to see how to basically do all those examples, but in C, Octave, or I guess there's other language, you can look there. You have plenty of examples done by Damien, actually. So now let's do this one. The same examples, but now with checkpointing, so implementing a very simple checkpoint here. So what I'm doing, at each iterations, I'm writing a file with basically the value of where I am, or the next number that I need to write. And when I'm starting my program, I'm checking if that file exists or not. And if it doesn't exist, I'm starting at 1. If it does exist, I'm restarting from there. But as simple as that. That's everything what is about checkpointing at the end of the day. It just restart from where you are. So obviously very, very simple, not very interesting, I would say. Just I'll run the program, as I said. Now at each iterations, so if I'm doing an ls here, you will see that the state file here is updating in real time. And then if I'm doing a cat of it, we'll see that currently it's at 20, which is the correct number. And now if I'm doing Control C, I'm killing the job. And now my file will indeed show 24. And then if I'm restarting my program, if it wants me, oh, I'm losing something. Okay. Let me kill the terminal. So yeah, I was typing and you were not seeing anything. Yes, and then if I'm restarting my program now, of course it will restart when you're stopping, so 24. So really no surprise here, nothing that interesting so far. So that's the simple things that typically what developers are going to do, including basically a checkpoint after each iterations, every big step of the work. Of course, this example is very simple. But what would be interesting is to not only save at each iterations, but also save when needed, or when, basically, you can, of course, decide. And basically, having the way to save the states where needed, and therefore you need kind of a signal telling you, oh, save now. And for that, we'll use what is signal, and in Unix, any process can receive a signal, and you're actually used to that. I mean, you are typically doing that every day. Okay, someone asked to post the link of the Indico website. Damien, can you do that, please? So yes, so basically you are used to that, because as a user, you're typically doing it. I already done it during these presentations, actually. You know that if you want to cancel something which is running, you can do Control C, and that's a signal sent to the jobs to basically stop it. Control D is typically for interface, to quit interface. You're typically also using Control Z to basically make a program to sleep. And then you have all those kill command, which is basically sending signal to the jobs. You typically use kill -15, which is a default, or kill -9. And you also know very well FG and BG probably to be able to continue your jobs in background or foreground. So that is something that after you are used to it, you probably also, the OS can send a signal. So for example, when there's a segmentation fault, it's going to signal that with a signal, or a broken pipe, which is the most too common one, let's say. But you can also send them by other process. And in any case, when the program receives a signal, it will do something with it. And either you can define what it does, or there's a default actions, which is most of the time to quit the program or just ignore it. That's, of course, depends on what you want to do. There's two signal, which is quite, let's say, particular, which is called signal user 1 and signal user 2. And therefore, it's redesigned actually for you to customize. So if you want to send a signal to any jobs to do something fancy, that's the two signals that you need to handle, to use actually. Because of course you can, and we'll do that, change what's happening when Control C. At the same time, when a user do Control C, he expects, of course, that the job is going to cancel, and you have to do that. You don't have to, but it's better, obviously. So if you want to do something very fancy, using signal user 1 and signal user 2. So let's show how to do that. Okay, what's going on? Okay, I'm back. And again. Okay. So in Python, so that's where the syntax change, of course, quite a lot for different languages, and we'll see later how to do that for Bash. But in Python, in order to specify how you handle a specific signal, you need to use a signal library. And what is that this is the name for Control C. SIGINT is the default name. That's the name for Control C. So what it's saying is that when you use its Control C or someone else is sending that message, that signal, then you are going to execute these functions. And the functions is designed here. And the only thing it does is change the global variables, which is interrupted. Is changing from false to true. So that we have now a global variable that's saying, is the user hit Control C or is the message was sent or not? Then if that global variable is on true, then we basically stop the loop. And then now we don't update the state file at each iterations as before, but we only do at the end of the file. So at the end of the script, we say at which stage we stop, either because we end basically the 500 iterations that we were targeting, or simply because the user sent Control C. And in order to have nice bash output, if it was interrupted, we return an error code 1, just so that it's nice. And as before, if the file already exists, it will be our case now, we start to count what the file is. So now if I run my program, I restart from the last steps. So it was 32. The big difference now, what's my error? Yeah. So if I do a cat of state, the big difference compared to the previous example is that this value is not going to update on the fly. It's going really to wait that I'm going to cancel the job. So if I'm doing Control C, you will see that at this stage, just before quitting, actually, it has updated the file so that if I restart my program, we of course restart exactly from where I started. So this allows a bit more flexibility, basically, to basically only checkpoint where needed and now at basically any n second in your code. Yeah, no, I still have my terminal. Okay, so these are very simple stuff that you can do on your laptop, obviously, a simple demonstration so far. The real question is how to do that on HPC infrastructures and how to do that with Slurm, obviously. So one comment, I don't think Damien discussed that much about it, which is Scancel. And it has actually the options to not only cancel your jobs, but to send a signal to your job. So to basically send any signal that you want, can be Control-C, it can be signal user 1, it can be signal user 2, or basically anything you want in the huge list of signal that you can send, basically. So in order to do that, it's very simple. You do scancel -s, then you can put the name of the signal or the number, and then of course you need to specify the job ID, and then you will send in this case, Control-C to your jobs on the clusters. So that's great if you want to trigger, for example, a checkpointing by hand, but in practice, that's not something you want to do, I guess. Another options in the same idea, in a way, so sending signal to a job, is the ---- signal options from SBatch. So you can put that into your bash scripts. We'll see in the next slide how to do that. It has three basic kind of arguments. So the first one is, of course, which type of signal you want to send. So in this case, in those two examples here, I'm using SIGINT. So again, it's Control-C. Then after the @ which is optional, you can specify how much in advance compared to the wall time you are going to send the signal. So here, the real idea is to send a message, a signal to your jobs, a given second, typically 60 seconds before your job is going to be killed by the wall time. So that's the main idea of that, so that we can basically do your checkpointing and then either you stop there or even resubmit your jobs automatically, as we've seen in the previous presentations, and I will demonstrate in a couple of seconds. The last argument is this B column, just where you send the signal. You can either send to the bash scripts, and that's the B, so that's this first line, or you run directly to the srun command within that bash script. So that's a bit up to you. You can basically decide I'm doing in bash or I'm going to handle inside my Python code, up to you. So Daniel already mentions that earlier. So of course, if you want to do checkpointing, it's important that you typically open your file in append mode, or your log at least, so that you basically keep track and don't overwrite the same file again, and then that you don't lose information. So that's one of the key points, the append mode. Also here, the srun is mandatory because I'm doing the ---- time. No, it's not this one. It's ---- signal. I don't specify the B information, so is going to be sent to the srun. If you don't have any srun, it will not be catch, obviously, at all. So the srun in this case is mandatory. So let's do the demonstrations. So in this case, I've opened my file in append mode. I'm putting a wall time, which is extremely short, of course, on the demonstrations, so a wall time of 1 minute. And I'm going to send Control-C to my Python code, which is exactly the same Python code I demonstrated before, which handling the Control-C, around 30 seconds before the wall time. So of course, it's Slurm, so everything will not be exactly 30 seconds. You have basically an uncertainty of 20 seconds of those, which is in this case quite large compared to the wall time in practice. That's not an issue. And I'm running in the debug mode and actually have my own reservations to be sure that I have allocations and that everything's run quite quickly. So let's do that. submitted. So now I'm going to watch SQ minus U on that, so that we can see here, basically in real time, what is the allocation status. So in this case, it's R, so running. And let's check where it's out written. So we do tail minus F test.out. You will see that it was running up to 92, then it was canceled due to the wall time. Indeed, you see that it's not running anymore. So now if I'm resubmitting it, do the tail, it will of course restart from 92. Everything there is handled in Python. But the main point is that I didn't have to do the checkpointing at each second. I'm doing the checkpointing basically only when Slurm is telling me, okay, your job is going to be canceled, and I'm checkpointing at that time. So that's, it's really close to the wall time, and I'm knowing that I'm not losing any computations at all. So obviously the annoying part here is that my job is canceled and I'm resubmitting it by hand, but you can fix that quite easily, and you have already seen the syntax earlier. I'm going to show it to you. So the only difference here is actually here. I'm going to execute scontrol requeue if that executable crash, and that means if the end code is not 0. And I've set up that code carefully, is that if there is the checkpointings occurring, then the encode is 1, and therefore it will requeue automatically the jobs. Important, obviously, here the mode happens as said before, and nothing to say more. You will keep the same job ID because it's scontrol requeue here. So let's do that. So it's running directly because I have reserved allocations, obviously. And I can do the tail. So I'm still continuing the same jobs. You see here that my job is canceled simply due to requeue. And you can see here on the right that I have a new jobs with the same job ID, which is just waiting to start. So when there's a requeue, you always have a couple of minutes, or let's say downtime, so where your job is not allowed to start directly, just to avoid basically that if you have a job that is crashing directly, you have kind of a lot of stress basically on Slurm. Here I'm using my sudo write to basically increase the priority of my jobs and to telling that it's actually can run now so that it can run directly. In practice, of course, you will have to wait, but for demonstrations, I don't want to wait the couple of minutes Slurms imposed to me, basically. And you see, of course, it restarts as usual, exactly where it starts. So that's really on the flight checkpointing just before the wall time. So that's a perfect setup for checkpointing for wall time, right? So the first big issue is that, I'm not allowed to run more than, let's say, 6 hours on some partition. This is the case of this one, actually. How do I do that if I have a job of, let's say, 12 hours? Then you basically let him run. At some point, Slurm will decide to kill your jobs. Before that, sending the signal, you do the checkpointing, and then it's requeue automatically. And then now you can, I can technically wait for this to continue. And I know that it will reach 500. I don't have to monitor it. Of course, I can launch the next iterations, but you basically just have to wait your jobs and to be allocated. Your job with 12 hours, you can say, let's say, in 14 hours, your job will be done. Depending, I count 2 hours for the time to allocate the slots, which is probably too long, but okay. Okay, let me cancel all my jobs now. You can also do the same, so requeuing automatically. Okay, I already submitted. with a slightly different syntax. So in this case, instead of sending the signal to the srun, so to Python, I'm sending actually the signal to this bash scripts. So the syntax is slightly different to catch the signal. In this case, I'm using signal user1, and I'm trapping, catching the signal user1, and I ask bash to execute the function's timeout when the signal is sent. So that will be around 30 seconds before the hold time. And what are the two functions I'm doing? I'm sending Control-C to my srun command, which is here, and I'm directly requeuing the jobs here. So it's basically the same as automatic requeuing, just two different, slightly different methods in order to do it. One thing is important in this case, since the message, the signal is sent to the bash scripts, I need to put this ampersand here to basically be sure that basically it's not blocking, and therefore I need to put the wait to say I need to basically wait that this is finished, but that allow basically the bash scripts to take the signal. So that's the typical solutions when you want the bash scripts to take the signal. You need to basically do this ampersand, which is quite important, and this wait, otherwise your job will finish directly. Is it possible to specify the number of requeuing actions if a run has to be run 4 times 6 hours? Yes, you can put if statement basically. I actually have the variables here. So you have this variable which will be updated. If I'm looking at the log, you will see that basically which is the value of this slum restart count. Therefore, you can put an if statement and prevent any requeuing after that. That's I guess the most easy solutions. You can check slum documentation, so maybe Damien knows if there's a way to specify it with this. It might be possible, I don't know. But otherwise, what I would do first is just to put an if statement, and that if slum restart count is bigger than a given value, so in your case, 5 or 4, then don't resubmit your jobs, basically. So that will allow you to basically avoid to have an infinite loop and your jobs respawning indefinitely, obviously. Okay, so this is what the file symmetry that I just described with this bash, in this case, this B, which is sent to the bash, this signal user1, which is catched here, exactly what I said. Don't forget, because I've seen that very often, this ampersand and this wait, typically that's what's confused people. It's really important here because you need the bash to be waiting for a signal, and therefore that you are not stuck within one of those comments here. Okay, and I already did that demonstrations. So this is the part about Slurm, which is basically showing you how to handle signal so that you can do checkpointing on the fly when needed. So the next part of my talk is about, okay, it's nice, so that's allow user developer, let's say, to handle that correctly. But there's one huge class of problem that is more problematic in a way, is that how do you do that for a program like, let's say, Mathematica, like a program where you only have the executable, but not the source code, where you cannot interact, and where it's not implemented. So basically, how to checkpoint a program which is not designed for checkpointing. And there are multiple solutions that exist, obviously. The one that we advise, and that's typically the most advice on HPC community, is DMTCP. So DMTCP, it stands for distributed multi-threaded checkpointing. And when you see in the documentation, so that's a snapshot of the website, they do checkpointings with no modifications to the user code. So that's not where it stands. You don't need to modify your code, you take your code as it is, and it's redesigned for HPC. That means they support MPI, Slum, fast networking like InfiniBand, and so on and so on. So that's really designed for you. On HPC, you have your code, you basically snapshot all the memory all the file which is open and stuff like that, and then you can restart from there. So maybe here, as you see, the announcement in the news stopped in 2019, which is quite old now. So they are doing a new versions of the MTCP since a while, to be honest. So I'm not fully sure if it's going to happen or not. And since actually also, if you know some people interested in joining, looks like they have PhD programs available. So what are the features? I already said quite a lot of features. One is, which is important, it's completely in the user space. So you don't need to be root, you don't need any special privilege. It can really run basically for any user on your cluster. So that's really nice. It works with quite old Linux kernels. So that's fine as well. And you can run MPI you can checkpoint MPI program like this. Good license and stuff like that. So they are also quite confident, let's say, about the program, and they say that if something doesn't work, if you don't succeed to checkpoint your program, that means there's a bug on our side, and of course, then in that case, open a bug report and we'll fix it basically. So here let's go back to our first original program. So in this case, it's in C, but I will use the Python one. So this is the original program where there is nothing inside the program itself for checkpointing it. And let's assume that we have this program in C where we have the executables, but we don't have the source. For whatever license reason, we cannot modify the source, or we just don't know C, but we want to checkpoint the program. So here in this case, this program is just doing count. So in this case, you are not going to launch your program normally. You are going to launch your program via the MTCP, via the MTCP launch, actually. And it will do under the hook a lot of namespace mapping and stuff like that. And I'm not going to enter into the details, and I don't know all of them actually. But it's basically going to track what is open and track the memory, obviously. But in a smart way so that it can also actually be moved on another computer and restart a lot of stuff there. So let's do demonstrations. Yes. So let's quit here. This is still running. I'm going to cancel it. So that was the previous job, actually this one I submitted and never look at the outputs. Maybe I can do it now. Maybe I should do a cat. Better. And then you should see here the requeue at some point. Yes, restarted 3, that's the number of requeuing in my script. And to come back to the answer, that's how you can basically trigger a special behavior depending if it's the first requeue, the second requeue, and so on and so on. So let's cancel. The previous jobs. Okay, perfect. And now I want to run this. So here, what I'm doing, I'm launching my counterreach.py, so that this is my original Python script, which doesn't even checkpointing in it. I put Python here, but it really can run C, pure executables, whatever, program you can run basically. You just start with the MTCP launch. Okay, oh yeah, I didn't set up the environment. And then I'm going to wait 4 seconds, and then I'm going to run this command, the MTCP command ---- checkpoint. So I'm going to ask the MTCP to do a checkpoint after 4 seconds. I'm putting an echo to make sure that it's occurring. Then I'm going to let it sleep a bit, and then quitting the program. Now, obviously, the first thing you need to do is to install, have the MTCP install. So in your case, I need to load the module. DMT. Of course, the module to have it available depends on your cluster. sorry, this was done before, but since I have issue with my terminal, I unlog and relog multiple times, and therefore I had to reboot that. And now I can run this. You see that it counts up to 4.3 in this case, then doing the checkpointing, then it's continue, then it stops after a couple of seconds. So now if I'm looking to the directory I have two new files, actually three new files. I have this one, which is basically a dump of memory to make it simple. And I have scripts to restart it with some crazy name associated to it. And then I have a more simpler script to start, which is DMTCP restart, which is a symlink actually to this one. So that script will always point to the latest checkpoint available, and that's making stuff convenient. So now if I want to restart my code, I'm just doing DMTCP restart script.sh. And now, of course, I'm not going to restart from one, but neither from the latest value I had, which was 7. I'm restart from the checkpoint, obviously. So that means I'm starting at 4. But without changing any line in my code, just launching my program with this DMTCP launch, doing this DMTCP command -- checkpoint, I was doing a checkpointing and being able to restart from that. So very practical stuff to do. Now I'm doing Control-C, so I have canceled the job. So now the question is how you do that on Slurm, on HPC infrastructures. And there are some complexity associated to at least our cluster in this case. That's why I said here that's something which is limited specific, which is actually the fact that we like, and a lot of clusters do as well, why to do, what to say it, a C group, so that we actually prevent you to use more resource than are allocated to you, both in terms of CPU and in terms of memory, so that you know that if someone else is running on the same node as you, you will basically not interfere, and that everyone has a memory and CPU exactly allocated to them. Otherwise, if it's not in place, you typically can have issue because someone else is taking all the memory of the machine and stuff like that. But the issue is that it puts some constraints on DMTCP, and therefore that's why we need some specific flag in this case. Independently of that, so this is the job that you can launch on your clusters. So obviously you still have to have the open mode append exactly like discussed a couple of times. In this case, we don't do we do a regular checkpointing, so a checkpointing every, in this case, 30 seconds. And for that, we just launch the DMTCP coordinator. So that's the trick. We launch a coordinator and tell him to do a checkpoint every 30 seconds. So that's what is the -- interval 30 is about. Of course, the &A to not block your program. One thing which is also important is to basically set the DMTCP host variables. That's especially important if you're going to change between different hosts. If you start on one node and you restart on the other one. After that, at least at the first executions, you run DMTCP launch and your program. There are two specific features here. The --rm, that's for resource manager. So that's allowed to tell you that your job is going to be submitted by Slurm in this case, and therefore it will going to be resubmitted automatically. So that's why here you don't need to have the explicit requeue. This -- resource manager is going to do that for you. And as I said, we need to handle some issue with the C group. Sorry for that. And therefore I'm doing -- allow file override, and this file 10 going to & and 11 to %. And that's only specific to C group. If you have C group on your HPC clusters, then you need to do that as well, obviously. If you don't, are not constraining the C group, then you can remove those rep blob. So I see questions. Does the checkpointing through DMTCP work with program making use of GPU as well. More specifically, do you know if the snapshot of this V makes consider GPU memory as well? I'm not 100% sure here. I've never done it, to be honest. I've seen the documentations that they say that they have plugins for that. So maybe you need to install those plugins and check the documentation. It's certainly possible, at least with plugins, but it's not 100% clear, and I never tested, so if it works out of the box there, but it's certainly possible. Okay, so let's do further demonstrations here. So this is exactly the same file, I mean, or very close as before. I have here a hold time of a bit more than 1 minute. That's my output file, opening in append mode, loading the DMTCP module and the Python module, launching the coordinator and an interval every 30 seconds, telling how much requeuing is occurring, obviously. If the file DMTCP restart exists and that I'm not at the first iterations, then I'm running that file. Otherwise, I'm starting DMTCP launch, this resource manager to having the requeue automatic, and then my programs, and this as discussed before. So now I can submit that. So you will see the job starting directly. So it will run for around typically 1 minute. I can do a tail of the output, which is LLS. I don't remember the name. Slam DMTCP. Just counting. Here is a small buffer, so you typically see numbers arriving every 3 seconds. I didn't succeed to a bit more real time, but okay, 3 seconds is more than reasonable. So it will run for around 1 minute, and after that, it will be requeue automatically, and then it will restart basically. Not from the latest value in this case, simply because I'm doing a checkpointing every 30 seconds. So in that case, it will start, should lose around 5 seconds if everything is perfect. So now it should cancel in principle now. You see that it's, I asked for 1 minute and 5 seconds, but Slam is not exact for the hold time. So you see that my job is still running when it's supposed to be canceled already. But that should arrive soon. And then as before, it will be put in pending because there will be a delay before it starts. So it's still not canceled. And then as before, I will use my sudo write to basically bypass that. Okay, I see in the meantime, then Damien link to an issue in DMTCP tracker on GitHub, so that where they discuss more in detail DMTCP and GPU. Okay, Slam doesn't want to cancel my jobs, looks like. Okay, so finally, and they show me the correct jobs actually. Okay, I'm not sure why this doesn't work this time. Is it finished? Or maybe it's finished actually correctly. I don't think so. No, it should not. Okay, so it looks like I made a mistake somewhere, but which is the demo effect because I ran the same script earlier this morning. It was working. Yes, everything sounds okay. Let me remove DMTCP restart.sh. Let me retry. I'm not sure what went wrong, to be honest. I have no clue. Okay, let's see if it works now. Because this is surprising me quite a lot. Yes. No. Yes. Everything is fine. Yes. So I'm not sure. I mean, it should work in principle. As I said, I run these scripts multiple times in the last couple of days, and everything was working. So I'm not sure. Maybe I changed something without realizing during the demonstrations here. So let's check. But otherwise, I will move to the next example. Let's see. So that's obviously the annoying part that we need to wait Slurm to cancel the job. So I can already move forward. We'll see if it works or not. So the last example I want to show is to combine what we saw before with Slurm with the DMTCP, which is meaning I want to be able, of course, to do checkpointing every 30 seconds or every minute or hours, obviously, and be able to do checkpointing just before the wall time, so that you kind of have both capabilities to have a regular checkpoint in case of crash, in case of whatever happened, basically, and be able to always have to lose only a given amount of time. But you also want to have the flexibility to restart exactly just before the wall time, and that's using the signal and methods we've seen before. And of course, those two can be combined together. So in this case, it's basically the same script as we've run just before. The things you add is, of course, all the setup part. So all the setup for the signal. So in this case, we send the signal user1 to the bash scripts 60 seconds before the wall time. And therefore, we need to define a function's timeout in bash that is going to run when that function is going on, when that signal is going to be sent by Slurm. And therefore, we need to allow the catching of that signal by bash. And therefore, at the end of each command that is running, we need to have this ampersand to not bring blocking and the wait at the end of the scripts. Exactly what we've done before. And within these timeout functions in bash, what we do, we run DMTCP command checkpoint. So exactly the same commands we have run by hand before. Now we can do the DMTCP checkpoint that will do the checkpoint exactly where we are. And of course, we can combine that with the S-control requeue so that we're requeuing your jobs and doing the next iterations automatically. And as before, we still have this, in this case, 300 seconds, so 5 minutes comment where we checkpoint the code. So there's a question. I'm not understanding how the DMTCP creates a checkpoint and for the program to restart from this checkpoint if it doesn't have access to the code of the program executed. So it has access to the binary. Sorry. So it has access to the binary of your program, obviously, And it has access to basically all the files, which files are open, what are the communications and stuff like that. So it doesn't have access to the source code, but it has access to the code itself. It has access to the binary code. So that is what it's using, and to basically restart, it has access also to the memory, so it can dump the memory, and then it can restart actually from the exact same state. So if you take something simple where you only have a couple of memory and could execute it in the RAM, so you can dump that to a file, then restore that, and you can rerun from exactly where you are. That's basically all the algorithm works behind. Now, on top of that, you have a lot of complexity, let's say, with files which are open, with communications between nodes, and so on, with memory on GPU and stuff like that. So we only not have one memory space, but multiple memory space, and that's where it interacts. So there is also questions about Scancel. For instance, when Scancel, in this way, the user can effectively cancel its jobs and expect the program to handle the signal. Yeah, if you basically have, in this case, like you see on the screen, you can send user one to your jobs, and you know that will do the checkpointing. You probably need to define, in this case, a user two, so that you let the program continue and not doing the requeuing. That's a bit up to you, obviously, but that's how it works. So you can indeed, with Scancel, send a message to your jobs so that you can run the checkpointing via DMTCP. So DMTCP is also going to be used. I'm going to discuss about Singularity tomorrow, actually, and the next versions of Singularity, which is actually called Obtainer. We'll discuss that tomorrow. Actually, also we're going to support DMTCP. So that's how to checkpoint container in that case. Yes. I think I've answered all your questions here, actually. So let's go to the program, and this time it seems to have running completely, and now it's submitted correctly. You see that it was resubmitted in the job. So I don't know what went wrong to the previous demonstrations. I didn't touch, I guess, anything except maybe remove these scripts, which maybe was confused. So that's maybe the reason, actually, that I need to remove that script first. And that means the restart was restarting not what I wanted to run. So I guess that was the issue. I need to fix my script according to that. Now, just before finishing, I can run the demonstration code I just showed you. So that's slum DMTCP signal. And here, I'm just going to check the conditions. It's the same. So just to be sure, I'm also going to remove the bash scripts, just to be sure that I will not hit the same issue. And I need to do Scancel first so that I don't have any jobs waiting. Okay. So now here, that's the last script I'll show you. So that includes a checkpointing every, I'm not sure about how many, every 30 seconds, I think. I can take a look how much I've actually put inside the script. Of course, you can be, let's say, more generous. So every 5 minutes, actually, for a job which are not allowed to run 5 minutes, is a bit stupid, but okay. And then it will do a checkpointing just before the wall time. And I will let him run and check soon, just before finishing, if it was indeed working as expected. So to summarize, I think it's quite important on each PC that you don't restart from scratch. So you never click discard again, and then you save your computations. That will help you both in terms that you can request smaller wall times. So that's also smaller wall time. Requesting smaller wall times allow your jobs typically to run faster, to be faster being allocated. So that's actually gain you time at the end of the day. And therefore, for your submission script, instead of having one big that spans for multiple days, having multiple smaller ones that you check out, I would say periodically, it's typically a good solution, or via the signal, and is of course a good options. To avoid that, you need to manage them. A good workflow should be in place, and that means requeuing automatically. We've seen that in the previous talk, and I've made some live demonstrations here. And of course, you need to be careful to not lose your previous logs, so open the files in Apple Logs.